Once again, welcome, everyone. We are now done with examples number 1 to 3. That means we can finally move forward to our next example. Shown here is the statement of the problem. The picture represents one full floor layout where each compartment or room is provided with sprinklers. Unlike examples 1 to 3, this setup is more complete because it involves the entire floor plan, which means our calculation will cover multiple sprinkler lines connected throughout the system. For this problem, what we need to find is the total pressure and discharge requirement of the whole sprinkler system. That's basically the main goal of this example. It was also mentioned that the pipe used for the cross main is 2 inches, while the branches use 1.5 inches. Take note that the cross main is the pipe that runs along the hallway, and from there, the smaller branch pipes extend toward the individual rooms or sprinkler heads. Also provided in the problem are the values of the K factor and the C value. Remember that the K factor applies to the sprinkler heads. It represents the discharge constant that relates the flow and the pressure at each sprinkler. On the other hand, the C value is used for the pipes. It refers to the roughness coefficient that affects the amount of friction loss along the pipe. So as we go through the calculations later, keep in mind that K is for the sprinklers and C is for the pipes. The sprinkler in the living room is installed 100 millimeters lower than the others. This difference in elevation will affect the pressure demand calculation later on, since elevation changes can either increase or decrease the required pressure at that sprinkler head. Moving forward, let us now begin labeling the network of pipes. First, we identify the sprinkler heads, which are the endpoints of each line. Next, we label the fittings, such as the cross fittings and the T-fittings, which connect the different branches together. These labels will help us keep track of the flow paths when we start our hydraulic calculations later on. In total, there are 16 significant nodes in the network. Each node represents either a sprinkler head, a junction, or a connection point where the flow direction or pipe size may change. From the nodes, we can now determine the runs, or the individual pipe segments connecting each node. There are 15 significant runs in total. I started labeling them beginning from the furthest run, which is the one farthest from the water supply. Now, since we have 15 runs or lines, this means there will also be 15 separate calculations. We will begin with the run that has the furthest sprinkler heads from the water supply. To start, we first identify which sprinkler heads are the most isolated or those placed in the most remote locations. We already know that the water supply is definitely connected at node 16. So we will probably start with either node number 1 or 2. Objectively, we will start with number 1 because the pipe length from node 3 to node 1 is longer. It just so happens that it is numbered as 1, but that is only a coincidence. If this were done manually and not using software, you could actually assign your own numbering for the nodes, depending on the order of calculation you want to follow. We would then proceed to compute for nodes 7, 6, 5, 12, 11, and 14. After that, we can now deal with the cross T, or intermediate connections, or the sprinklers that are placed inside the lines. Okay, so since we have already laid down the strategy or the sequence of our calculations, we can now proceed with the next step. We will now lay out our tabulation. According to the National Fire Protection Association, this is the recommended tabulation format. This table is also known as the hydraulic calculation sheet, and it contains all the data we need. But for our discussion, we will modify it slightly so I can explain each part more clearly. So here it is. It looks almost the same as the NFPA sheet. We just added a few details. The columns include the following. First is the pipe number. Second is the flow or discharge. Third is the inside diameter of the pipe. Fourth is the equivalent length of pipe. Fifth is the pressure. And the sixth column is for comments. For the discharge column, small q stands for the individual discharge, while capital Q is the total discharge. Sometimes, if capital Q is adjusted, we also include a separate row called Q adjust. For the pressure, small p is the demand pressure of the sprinkler. P sub E is the pressure due to elevation. P sub D is the pressure drop. And finally, P sub T is the total pressure. If you want to show your step-by-step computations, you can write them under the comments column. Like we said earlier, this table format is just like the one in NFPA. After using our modified version, You can transfer your results into the official NFPA hydraulic calculation sheet if the computation is to be submitted. We will now start solving. As mentioned earlier, we will begin with node number 1. If you recall from our previous examples about sprinklers, we are supposed to use the AD formula for the discharge calculation. Take note of our designation. The line between nodes 3 and 1 has an area of 16.4 square meters. This value was taken from the given plan. In that plan, the area of room 2 is 16.4 square meters. Now we compare this area with the requirements of the code to determine the correct density. From the NFPA area density curve, we get different categories of occupancy ranging from light to extra hazard. There was no special indication in the problem statement about the type of occupancy. But judging from the plan provided, we can assume that the structure falls under the light hazard occupancy. In the NFPA area density chart, light hazard occupancies cover areas from 140 to 280 square meters. Since our given area of room 2 is less than the minimum, we will just use the density value corresponding to the minimum area, which is 4.1 millimeter per minute. With that said, we now compute the discharge requirement using the area density equation. Since the area is in square meters and the density is in millimeter per minute, we have to make sure that the final unit is in cubic decimeter per minute. To do this, we convert the area into cubic decimeters and convert the 4.1 millimeter into decimeter as well. We do not need to convert the time since it is already in minutes. This conversion is necessary because later computations require that our unit for discharge be in cubic decimeter per minute. After substituting all the values, we get the result for the discharge of sprinkler number 1. Since there are no other connected pipes, sprinklers, or fittings between nodes 3 and 1, we can say that the total discharge for line 1, 2, 3 is the same. Next, we will be using the K-factor formula for discharge. In this case, we already know the discharge value from our previous step. What we now want is the pressure demand value because it represents the required pressure at the sprinkler located at node 1. Knowing this allows us to compare it with the minimum pressure requirement in the code, which is 7 psi or roughly 48.263 kilopascal. This is the minimum pressure required by NFPA for a sprinkler to operate properly. So we rearrange the formula so that the unknown pressure is isolated on one side of the equation. We get P equals the square of the ratio of Q over K. The value of Q has been computed already, and the value of K is given in the problem statement. Always double-check the units before performing the calculation. It is good that we already converted the discharge to cubic decimeter per minute, which matches the unit of the K factor. This means the remaining unit after simplification will be kilopascal, which is correct for pressure. After computing, we get a pressure demand of around 60 kilopascal. This value is greater than the minimum required by NFPA, which means there is no need to adjust the discharge for sprinkler number 1. Next, we will deal with the pressure loss due to friction and fittings. The best way to do that is to account for the actual length of the pipe for that particular run. We also need to include the loss due to fittings, which we can determine by using the equivalent length of fittings as specified in the NFPA tables. We consider that there is a T fitting in node 3. Using table 28.2.3.1.1 of NFPA, we can determine its equivalent length. According to NFPA 13, 2022, table 28.2.3.1.3.1, we will have to adjust the value since the fitting is only schedule 10. Under NFPA 13, 2022, table A16.3.2, we can also find the inside diameters of steel pipes that we will use for the next computation. By adding the actual length of the pipe and the equivalent length of the fittings, adjusted based on the inner diameter, we get the total effective length of the run. From the same NFPA table, we can also obtain the inner diameter of the pipe that we will use in our pressure loss calculation. Next, we substitute all the given and computed values into the derived PD formula. Make sure that all the units are consistent. After solving, we get the pressure drop requirement. When this value is added to the pressure demand at node 1-3, we obtain the total pressure demand for that particular run of pipe. After completing all those calculations, we can now populate our modified hydraulic calculation table with the results for discharge, pressure, and equivalent lengths. We will now do the same set of calculations for node number 2. The area for sprinkler number 2 is 11.86 square meters. Since this is less than the minimum required area, we will use the same density value as before. Using the same area density equation, we compute the discharge and get a value of around 48 cubic decimeter per minute. Using this discharge, we can now find the corresponding pressure by applying the K-factor formula. We get a pressure of 31.8 kilopascal. This value is less than the minimum required pressure, so to comply with the code, we will instead use the minimum value of 48.263 kilopascal as the pressure going into run 23. Next, we reverse the calculation. Starting from the minimum pressure, we solve for the expected discharge using the same K-factor formula. This gives us a discharge of 60.093 cubic decimeter per minute. Node number 2 is a lone sprinkler, so the total discharge demand for run 23 is also 60.093 cubic decimeter per minute. We then determine the equivalent length of the run using the same method as before. Take note that run 23 will have the same type of fitting as run 13. We now plug all the given and computed values into the formula for pressure drop. After that, we compute for the total pressure demand for that specific run of pipe. And as always, once we're done with the calculations, we tabulate all the results neatly in our table. Next, we move on to run 3-4. Here, there is a pressure difference between the two pipes that branch out from node 3. The pressure going to node 2 is much lower than the pressure going to node 1. Now, since these two lines are connected in parallel, the pressure should actually be equal for both. To make them equal, we'll use the higher pressure as the reference for all the connected pipes. This means that the pipe leading to node 2 will adopt the pressure that goes to node 1. To do this, we apply an adjustment computation. The formula is a ratio and proportion between the adjusted and original discharge and the square root of the adjusted and original pressure. When we isolate the adjusted discharge, the formula becomes the original discharge multiplied by the square root of the adjusted pressure divided by the original pressure. Using this formula, we get an adjusted discharge of 67.3 cubic decimeter per minute for the pipeline that goes from node 2 to node 3. We then record this adjusted discharge value in our tabulation table. We are now ready to work on the supplying line from node 3 to node 4. It is expected that the total discharge flowing through pipe 3 to 4 is equal to the sum of all discharges leaving node 3. So that includes the discharge from pipes 1 to 3 and 2 to 3 along with any sprinklers connected in between. The total discharge is approximately 134 cubic decimeter per minute. Next, we solve for the equivalent or effective length of the pipe. Since there are no other fittings before pipe 3 to 4, its equivalent length is simply the actual length of the pipe. Also, remember that pipe 3 to 4 is part of the cross main, so its nominal diameter is 2 inches. Using the table, we get an inner diameter of 54.8 millimeters. Now that we have all the necessary values, we can proceed to calculate the pressure drop demand for this run. And as always, after completing the calculations, we record and tabulate all the results in our summary table. We now continue with the next segment of the cross main, the pipe that supplies water from node 3 to node 4 and onward to node 9. This next pipe segment is labeled 4 to 9. Since the pipes 3 to 4 and 4 to 9 are connected in series, we can assume they have the same pressure at their junction. So the pressure leaving pipe 3 to 4 will also enter pipe 4 to 9. We'll use that same pressure in the K-factor formula to find the actual discharge from sprinkler number 4. Then we add that value to the discharge from pipe 3 to 4 to get the total discharge flowing through pipe 4 to 9. Next, we find the effective length of the pipe. At node 9, there's a cross fitting, so we include its equivalent length based on the pipe schedule. After that, we can compute the pressure drop using the same pressure drop formula. Finally, we record all the results in our table, including the total discharge, pressure drop, and updated pressure at each node. Next, let's move on to run 7 to 8. This pipe shares the same coverage area as the one from 6 to 8, so we'll divide the total area by 2. That gives us the design area for this branch. Now, when we compute the pressure for this sprinkler, it turns out to be lower than the minimum allowed value, so, just like before, we'll use the minimum pressure to comply with the code. After that, we'll determine the effective length by adding the actual pipe length and the equivalent length of the fittings, adjusted for the inner diameter. Since this is a branch line, the pipe size is 1.5 inches. Using the table, we can get its corresponding inner diameter. Once all of that is set, we plug the values into the pressure drop formula, solve for the result, and finally record everything in our table. Now, let's continue with the next line, run 6 to 8. The process here is almost the same as what we did for run 7 to 8. They share the same area, so the same division applies. We again check the pressure, and since it also falls below the minimum, we'll use the required minimum value. Then we compute for the effective length, combining the actual pipe length and the adjusted length for fittings. This line also belongs to the branch network, so we'll use the same pipe diameter and inner diameter as before. Once we've gathered all the values, we calculate the pressure drop and update the table with the results. Now, since runs 6 to 8 and 7 to 8 are connected in parallel, they should have the same pressure just like what we did earlier. Between the two, the pressure on runs 6 to 8 is slightly higher, so we'll use that as our reference. To make them equal, we'll perform a discharge adjustment on runs 7 to 8. We'll use the same adjustment formula as before, the original discharge multiplied by the square root of the ratio between the adjusted pressure and the original pressure. After applying that, we get the corrected discharge for runs 7 to 8, and that value will now be used moving forward. This pipe 8 to 9 supplies the flows for the lines 6 to 8 and 7 to 8. The total discharge through pipe 8 to 9 is simply the sum of the discharges from 6 to 8 and 7 to 8. So we add the two branch flows to get the capital Q for the run 8 to 9. Next we consider the pressure drop along this run. Because there is a fitting at node 9, we must include its equivalent length in the effective pipe length. So the effective length is the physical pipe length plus the equivalent length of the fitting adjusted for the pipe inside diameter. With the total discharge and the effective length, we plug those values into the pressure drop formula and solve for the pressure loss. Once we have the pressure drop, we add it to the upstream pressure to get the resulting pressure at the downstream node. Finally, we record all values in our table, including the discharge for 6 to 8 and 7 to 8, the capital Q for 8 to 9, the effective length, the computed pressure drop, and the updated pressure. Moving forward, we will work on branch 5 to 9. This is almost the same as the previous isolated sprinklers where we use the AD formula to compute discharge. First, compute the area for this sprinkler and then use the AD equation to get the individual discharge. Next, account for the elbow fitting on this run. Add the equivalent length of the elbow, adjusted for the pipe inside diameter, to the actual pipe length to get the effective length. Also note that the sprinkler is installed 100 mm lower. Include this elevation change when computing the pressure demand. Remember that lowering the sprinkler reduces the required pressure, so we add or subtract the appropriate PE term in the pressure demand computation. After that, we plug the total discharge and the effective length into the pressure drop formula and solve for the pressure loss. Add the pressure drop to the pressure demand to get the resulting pressure at the downstream node. With all values computed, tabulate the results. Include the following entries in the table. First, the pipe run 5 to 9. Second, the individual discharge and any adjusted or capital Q. Third, the pipe inside diameter. Fourth, the equivalent and effective length. Fifth, the pressure demand including the elevation correction. Sixth, the computed pressure drop and final pressure. With that said, we can move on to the next run. Alright, so we move on to the cross main segment 9 to 10. This pipe supplies the flow that goes to nodes 4, 5, and 8. Since those lines are in parallel, their pressures must be the same. Among the three, the pipe from 4 to 9 has the highest pressure, so it will control the adjustment. To equalize the pressure, we adjust the discharges of the other two branches using the same discharge adjustment formula. That way, all three connecting lines will now have equal pressure at node 9. Once the discharge values are adjusted, we proceed with the computation of the pressure drop for the run 9 to 10. We use the total discharge that passes through it, the equivalent pipe length, and the inner diameter in the pressure drop formula. After solving for the pressure loss, we update the downstream pressure and then record all the results in the table. We still have a few more runs left to finish, so let's continue. Here is the full layout again. This will help us see where we are in the network and which parts we have already calculated. At this point, most of the branches and cross mains are already covered. We are now completing the remaining segments before moving closer to the source connection. Here we have the tabulated results for the remaining runs, from 10 to 13 and from 15 to 16. These values complete our set of calculations for the entire sprinkler network. By this point, all runs now have their corresponding discharge, pressure demand, and pressure drop properly accounted for. Here we can see the full tabulation for all runs combined. Looking at the last row, the total discharge is 711.046 cubic decimeters per minute, and the total pressure demand is 120.036 kilopascal. These values represent the final demand at the source or the water supply node for the entire sprinkler system. That would basically be the answer to example number 4. This is example number 5. We are asked to determine the required booster pump if the main tank supply is 3 meters above the pump, and to find the volume of the tank to use. The problem also states that the pressure loss from the source to node 16 is 4.331 kilopascal. Starting from the final pressure we obtained in example number 4, which was 120.036 kilopascal, we will solve for the required pressure at the pump. We will add the given pressure drop of 4.331 kilopascal and subtract the pressure equivalent of the 3-meter elevation. This elevation provides a positive head of around 29.43 kilopascal. After adjusting, the required pump pressure comes out to about 94.937 kilopascal. Next, we calculate the total flow demand of the tank. The discharge from the system is 711.046 cubic decimeters per minute. Adding an allowance of 100 gallons per minute, or around 378.541 cubic decimeters per minute, gives a total of approximately 1,089.587 cubic decimeters per minute. Assuming a pump efficiency of 60%, we can now solve for the required power. Substituting the flow rate and pressure head gives a power of about 2.87 kilowatts, or roughly 3.85 horsepower. Finally, to estimate the tank volume, we refer to NFPA 13/2022, Table 19.2.3.1.2, which provides the recommended operating time of 30 minutes for light hazard sprinklers. Using that duration, we can size the tank to meet the required water demand. Here is example number 6. I'll leave this one for you to solve on your own so you can practice the entire process we just went through. And that wraps up our tutorial. We have covered how to perform hydraulic calculations for sprinkler systems step by step, following the NFPA provisions. Take your time to review each part and try applying the same procedure to different layouts. Anyways, that would be it for now. See you in the next discussion.